Okay, in this video or series of videos, it's going to be my version of an AP Calculus summer assignment. These are the skills that I think you should come in with so that you're ready to go as soon as the school year starts. So here's a very broad topic list of things that I'm going to cover. So geometry concepts, trigonometry concepts, some algebra stuff. There's actually a lot of algebra stuff. Very few log things, but there are some that you really need to know. And then some limit things, which maybe it depends on your AP Calculus class. They might not expect you to come in knowing that. But if you do, doesn't hurt. So let's get started. All right, so geometry. There are some important area formulas that you definitely must know. You're going to use them over and over again, and everyone expects you to know them. So the first one is a triangle, any triangle. So the area of any triangle, here's a triangle for you. We have a base. We have a height, which is perpendicular to the base, and overall that's a triangle. It's going to be 1/2 base times height. You definitely know that. Now the next one is an equilateral triangle. You may not know this one, but it comes up in a particular application in calculus, and it's very useful if you know it. And so the area of an equilateral triangle that has a side, which I'm just calling side, is √3/4 times the side squared. So you definitely want to know that as well. All right, next up, a rectangle. Do you know what a rectangle looks like? I bet you do. It has a base, it has a height. The area of a rectangle is base times height. Not super surprising. Next up, trapezoid. Trapezoids are more important in calculus than you ever would have guessed. So here's what our trapezoids generally will look like in calculus. They are sitting on what you typically think of as the height, and the bases are vertical. So that's a little unusual. But the area of a trapezoid is half the height times the sum of the bases. So you may have learned that at some point in your life as the average of the bases times the height. What I want you to do is change the way you think about it to half of the height times the sum of the bases. All right, the next shape that comes up a lot and that you probably already know, excuse me, is a circle, right? So you know what a circle looks like. Circles have a radius, and that's about it. The area of a circle is pi r squared. And then in calculus, this other thing to do with a circle comes up kind of a lot. And it's a semicircle where you originally know the diameter. So we want to write the area of a semicircle in terms of the diameter of the circle. So here is our semicircle. I shaded it in because I wasn't sure what to do. I've labeled the diameter. All right, so the area in terms of the diameter is going to be pi/8 times the diameter squared. All right, so that's a little weird. So let me just show you that. So the radius is the diameter over 2. So a full circle would be pi times the quantity diameter over 2 squared, right? Pi r squared, which gives you pi/4 times diameter squared. But then a semicircle is only half of that, so that's going to give you your pi/8. All right, so those are the area formulas that I think you must know. Next up, similar right triangles. I know there's a lot to do in geometry with similar triangles, but in calculus, we pretty much only use similar right triangles. So let's see what we have here. I have a right triangle, and inside of it, I've drawn a new triangle where the base of this triangle is parallel to the base of my given right triangle. So I've labeled it big R, big H for the big triangle, little r, little h for the little triangle. And what you really need to know about this, and this will come up many times, is that big R over big H is equal to little r over little h. Regardless of what I know or what I need to solve for, I start with that. Big R over big H equals little r over little h. You know, you can do some things there. Start with that every time and you will be fine. All right, next up, some important volume things. I don't even know the last time you thought about volume because it doesn't come up that much outside of geometry and calculus. So first up, a rectangular prism. What do those look like? They look like, I don't know, shoe boxes, right? So I have dimensions of x, y, and z, and then my volume is just going to be x times y times z. That's a pretty good one. There's also just a right prism. So that was a rectangular prism that we just talked about. A right prism could have any kind of base, but you're going to go straight up, right? You get kind of like a, I don't know, a box that something might be sold in, right? They could have a triangular base. They could have a hexagon base. They could have whatever base you want. So we have a base, we have a height. The volume of this thing is going to be the area of the base, whatever formula that requires, times the height. That's a good one to know. Next up, we have a cylinder. So cylinders come up a lot in calculus. So you have a radius and you have a height, basically, for a cylinder. And our volume is going to be pi, the radius squared, times the height. And then the final volume that I think is really important is a cone. So when you have a cone, cones, I'm not really good at drawing, so I basically do a circle with like a triangle at the bottom. It has a radius, it has a height. The volume of a cone is 1/3 pi r squared h. So it's 1/3 the volume of the cylinder is how I've always kind of remembered that. These are the 4 main volumes that you will need to use. I mean, the right prism is almost any volume, so that covers kind of a lot of them. All right, next up, there's another cone thing that you should know. And the cone thing that you should know is that when you have a cone, you can draw a little right triangle inside of it. This is key. You're going to be doing this quite a few times. So you draw this little triangle, and then within that triangle, you can do the similar triangle thing. So it's actually the similar right triangle thing happens within a cone, which means for this, I'm going to go with big R over big H equals little r over little h. So that, I know we kind of flew through it. Those are the geometry things that I think you need to know going into calculus. All right, next up, we're going to talk about some trigonometry things. The first one, all of calculus is going to use radians. Change your calculator to radian mode right now and leave it there. If you're in physics, you're probably going to have to switch back and forth, but keep that in mind. All of calculus uses radians, so make sure you're in radian mode. All right, trigonometry, SOHCAHTOA, all over the place. Now, mostly you just end up using the functions, and you kind of just set up the ratios and go. They're going to be in terms of variables for the most part, but here's what happens. We have a right triangle, and there's an angle I'm calling theta. There's a side opposite, there's a side adjacent, there's a hypotenuse. So this you should know because this is a review video, but sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. All right, so those are the basic things. You also need to know cosecant, secant, and cotangent, but you don't need to know that cosecant is hypotenuse over opposite. I mean, you should know that, but I prefer to think of it, especially in a calculus point of view, as cosecant is just 1 over sine, and then secant is just 1 over cosine, and cotangent is 1 over tangent. So you will use those relationships frequently. You need to make sure you know them. That's kind of the SOHCAHTOA that you need to bring with you. Now, there's 2 other things that are extremely helpful to know, and they are that tangent is sine divided by cosine. You will use that a lot. That's called a ratio identity. And also, similarly, because cotangent is 1 over tangent, cotangent is cosine over sine. You'll be seeing both of those. You'll use them when you're solving problems. All right, the next thing, trigonometry based, that I think you need to know is maybe not trigonometry. It's probably actually geometry, but I thought it belonged here the most. Pythagorean theorem. If you don't know the Pythagorean theorem, you're going to struggle in calculus. So the Pythagorean theorem, here's a right triangle with sides a and b and hypotenuse c. We all know is a squared plus b squared equals c squared. But in calculus, you will frequently use this as x squared plus y squared equals z squared. You're going to use it in distance problems. You're going to use it in problems that involve ladders, all kinds of things. Pythagorean theorem is going to come up. Now, almost every calculus problem that you do that is non-calculator at least is going to come down to a special, not a special right triangle, although those are important. It's going to come down to Pythagorean triples. So make sure you know the famous Pythagorean triples. So those are 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. Those are your Pythagorean triples. Make sure you know them. They will save you a ton of time. And also, when you're doing a problem in calculus and you see 5 and 13, you basically know that 12 is in the problem somewhere. Like, you want to have that in mind as you're doing these things. All right, next up, big one, the unit circle. Now, some people will tell you you don't really need to know the unit circle. I completely disagree with them. Although you can get by without knowing it, why would you choose to do that? It's going to take you like 5 minutes to learn this thing. And once you know it, you have the privilege of using it on every problem, and it makes so many problems so much simpler. So this is our unit circle. It took me a really long time to make that, maybe an embarrassingly long time to make that. And on the unit circle, The x-coordinate of a point is cosine of theta. The y-coordinate is sine of theta, which means each ordered pair is cosine theta comma sine theta. Now, I will confess, when I was in high school, the only thing that I used the unit circle for was the quadrantal angles, 0, pi over 2, pi, and 3 pi over 2. But I use it for everything now. Here are the ordered pairs that are associated with that. So 0 is 1, 0, and then we have 0, 1, negative 1, 0, 0, negative 1. Extremely useful for finding the sine, cosine, sine of all the quadrantals. I've always used that. Now, the other angles, there are 17 famous angles. They are the pi over 6, pi over 4, pi over 3 angles. I'm going to group them together. So we have our pi over 6's, pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. All of them have ordered pairs that look almost identical. They are root 3 over 2, 1/2, negative root 3 over 2, 1/2, negative root 3 over 2, negative 1/2, and root 3 over 2, negative 1/2, missing a negative, tragedy. Hold on. I knew it was going to happen. There's too much stuff in this for me not to mess up somewhere. All right, so we got that. Now, those are your pi over 6's. Let's move on to the pi over 4's. Your pi over 4 angles are pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Okay, now when you're dealing with those, they have the best ordered pairs because they have basically the same x and y. It's just pluses and minuses that are going to change. You're going to get root 2 over 2, negative root 2 over 2. Sorry, root 2 over 2, root 2 over 2. Negative root 2 over 2, root 2 over 2. Negative root 2 over 2, negative root 2 over 2. This is hard to say. Root 2 over 2, negative root 2 over 2. So I'm going counterclockwise, quadrant 1, 2, 3, 4. We got pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. All the pi over 4's. Next up, the pi over 3's. Pi over 3's are my least favorite for literally no reason. We got pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. All right, so once we have these, we need their ordered pairs. Their ordered pairs look an awful lot like the ordered pairs for the pi over 6's, except we swap the x and y coordinates. So we're going to get 1/2 root 3 over 2, negative 1/2 root 3 over 2, negative 1/2 negative root 3 over 2, 1/2 negative root 3 over 2. That's the unit circle. Take a couple minutes, memorize it. You'll be able to refer back to it in your mind. It's phenomenal. Highly recommended. All right, next up. You need to know the graph of sine. I have a lot of videos about the graphs of sine and cosine and how to create them, but you don't need all the transformations in my experience. What you really need to know is, can you graph sine? Can you reflect it over the x-axis? And can you change the period? Those seem to be the most important skills by far as AP Calculus is concerned. So let's take a look at what just sine looks like, right? So we have our grid, and then we have the normal period is 2 pi, so you have 2 pi, so it goes pi over 2, pi, 3 pi over 2, 2 pi. And then we just fill in our curve. So it goes intercept, maximum, intercept, minimum, intercept. Sine starts at an intercept, goes toward a maximum, which means negative sine is going to start at an intercept and go toward a minimum. That's kind of what you need to know. Now, also, you need to be able to change the period, as I mentioned. So we would have y equals sine of bx. Now you're going to change the amplitude, things like that, but you're not really going to be shifting it up, down, left to right in my experience. It's good to know that. You could definitely review that, but this is the big stuff that you need to definitely know. So here, our new period is going to be 2 pi divided by b, which means all of those tick mark things, what the increments, are just divided by b. So we are going to end up with a graph that does this. So instead of ending at 2 pi, it ends at 2 pi over b, and then you're going to get pi over b. So you go pi over 2b. It's easier if you actually have numbers. I'm going to do that in a second. But you basically just take everything and divide by b. That's the idea. So here's our graph, same exact graph. All right, here's a couple of examples where I've changed it. So I did y equals sine of 6x. So I have 2 pi over 6. So that means that's pi over 3. Pi over 3 divided by 4 is pi over 12. So I counted by pi over 12s. Pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12. That's pi over 12, pi over 6, pi over 4, and 2 pi over 6, which is pi over 3. Then I had sine of x over 5. So 2 pi divided by 1/5 is 10 pi. So I have 10 pi divided by 4 is 5 pi over 2. Count by 5 pi over 2. 5 pi over 2, 10 pi over 2, 15 pi over 2, 20 pi over 2. And that gives us our graph there. And then I had sine of pi over 2 times x. That's actually really common to have pi in the value of b. So I do 2 pi divided by pi over 2, which just gives me 4. 4 is really easy to divide by 4. So we go 1, 2, 3, 4, and it's the same basic shape. So that's an important thing to know. Next up, you may have guessed, is the graph of cosine. So when you have the graph of cosine, you just have to know it. This is a review video, right? So I'm kind of assuming that you know these things and you just need a little refresher. So, or I'm really telling you the big ideas that are super important and you have to hold on to. You can't afford to forget anything that's in this video. Other things kind of slip a little, maybe you review them every once in a while. This is the stuff that needs to be front of mind all the time. So here's cosine. That is not the graph of cosine. That is the graph of sine. This is terrible. Hold your horses. Let me, on the fly, I'm going to change it up so it goes. Struggle. So cosine starts at a maximum, goes maximum, intercept, minimum, intercept, maximum. I'm going to have to change the next one because the next one I screwed up too. You know, this is what happens when you copy and paste between your slides. The next one I'm going to graph is negative cosine, which switches all of the maximums and minimums. So watch me do this and watch me fix it. So I got to go delete, 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 and delete. All right, we're going minimum, intercept, maximum, intercept, back to a minimum. And I'm going to try for it. Here we go. Should have looked this over again. You know, I never would have caught it. That's what happens when you're making videos. You think you've got it down, you don't. So negative cosine just switches everything. Our period is still 2 pi because I didn't change the value of b. You're going to have to do that for cosine as well. Now, where do these really shine in calculus? They really shine when you're trying to make sine charts. So sine charts are basically number lines where you put pluses and minuses. So for example, you might be asked to figure out when sine of 5x over 2 is greater than 0. Well, to me, that means what does the graph of sine of 5x over 2 look like? So if that's all I'm dealing with, I know that the period is 2 pi divided by 5 over 2, which is 4 pi over 5. I divide that by 4, which just gives me pi over 5, so I have 0, pi over 5, 2 pi over 5, 3 pi over 5, 4 pi over 5. Sine, generally speaking, does this, and then I'm going to fill in my pluses and minuses. So these graphs, knowing them, is going to allow you to fill in these sorts of sine charts really quickly with things that you already know. All right, next up, we're moving into some algebraic stuff. So it's going to be the properties of exponents. Sorry, that was the answer to that question. Properties of exponents. All right, number one, if we have x to the a times x to the b, we're going to add the exponents. So same base multiplying, add the exponents. X to the a times x to the b is x to the a plus b. Number two, x to the a over x to the b is going to be x to the a minus b. So same base, dividing, subtract the exponents. Next up, now I think this is an important one, I use it a lot. X to the a over y to the a is the quantity x over y to the a. So if you have different bases but the same exponents, you can bring them all into one set of parentheses. Next up, I like to refer to this as power to the power. So we have x to the a raised to the b. That's going to be x to the a times b. You use that property a lot in calculus when you're simplifying things or unsimplifying them. Next up, if we have the quantity xy to the n, everything gets an exponent, right? So you're going to get x to the n times y to the n. Those are your properties of exponents. Now, there's one other thing that I think of as exponents, but maybe other people don't necessarily think of as exponents, and that would be something to do with radicals. So I think that radicals are terrible and that you should always rewrite them as rational exponents. So if you have the nth root of x raised to the m power, that's going to be x to the m divided by n. So I would say that in calculus, rational exponents are almost always going to be better than radical notation. All right, other things that you need to do in terms of algebra stuff. You might need to factor. Actually, you're going to need to factor a lot. I'm going to be assuming here that you can factor a factorable trinomial, right? Like ax squared plus bx plus c. You're going to have to factor a ton of those. There's a lot of examples of that on the internet. You should go find those if you're not super good at those. Now, in this, I want to talk about difference of squares, which is x squared minus y squared. We can factor that into x minus y, x plus y. Comes up a lot. Now, the other thing that comes up like all the time is factoring by grouping. You will find yourself factoring by grouping a lot, so much so that I'm actually going to do 2 examples of it in this video. So this will come up all the time. So for example, we might have, also I couldn't really decide how to like describe it other than doing examples, which is part of why I'm doing examples. I have x plus 3 cubed times x minus 2 squared plus x minus 2 cubed times x plus 3 squared. So there's a lot of similarities there, right? X plus 3 and x minus 2, factors of both. So I can take out an x plus 3 squared because that's the lowest power of x plus 3 that I see. So I'm going to take that out. I can take out an x minus 2 squared because it's the lowest power of x minus 2 that I see. They share that. So I'm going to take those out, and then I will be left with, from the first thing, an x plus 3, from the second thing, an x minus 2, which means that overall, this will factor into x plus 3 squared, x minus 2 squared, times 2x plus 1. There's something that we do in calculus that leads to this scenario quite a bit. It's called the product rule. And it basically creates these types of problems, which is why this type of factoring is so common. All right, next up. 8 times the quantity 3x plus 1 squared times the quantity 2x plus 5 cubed plus 6, the quantity 2x plus 5 to the 4th, the quantity 3x plus 1 to the 1st. All right, so I look at this and I think I could take a 3x plus 1 out of both of those, and I can take a 2x plus 5 to the 3rd out of both of those. So I'm going to do that. Also, 8 and 6, I can take a 2 out of that, so I will do that as well. So I'm taking a 2. I'm taking a 3x plus 1, and I'm taking a 2x plus 5 cubed. Now we just look at what's left. So from the first term, we're left with 4 quantity 3x plus 1. From the second term, we are left with 3 quantity 2x plus 5. And then we just simplify this. There's really nothing to do with the first 3 things, but then that last set of parentheses, we can simplify into, I believe, 18x plus 19. So we get that. All right, the next thing that I think is super important that we should know how to do is rationalize a numerator or a denominator. So we want to rationalize one or the other. Now, I didn't know how to explain this other than doing examples either, so I'm going to do that. So if we have radical x plus 3 minus 2 all over x minus 1, what I'm going to do is I'm going to multiply by radical x plus 3 plus 2 over radical x plus 3 plus 2. I'm multiplying by the conjugate of the numerator. I am rationalizing the numerator. So that's going to look like this. Now, when I do that, I end up with the quantity x plus 3, because it's radical x plus 3 squared, so that just gives me the quantity x plus 3. And then I have plus 2 times negative 2, which is minus 4. The middle term's canceled, so I have this. Now, if you look at this, x plus 3 minus 4 is x minus 1. The x minus 1's cancel, and I am left with this, provided that x is not 1. So this is a scenario that actually will come up a surprising amount. There's a lot of stuff I'm telling you is really important that may be surprising to you, but let me tell you, I've done a lot of calculus. These are the things that come up that you really need to know. Now, what if we need to rationalize a denominator via example? So we have x minus 9 over radical 2x plus 7 minus 5. I need to rationalize this, multiply the top and the bottom by the conjugate of the denominator, so this. Now, when I expand it, I'm going to get quantity x minus 9 times quantity 2x plus 7 plus 5. If you're rationalizing the denominator, do not expand the numerator. If you're rationalizing the numerator, do not expand the denominator. Trust me. The reason that you're doing that is that you want to actually like cancel something, basically the other one. So let's continue here. So I'm going to not, I'm rationalizing the denominator, so I need to expand that. So I have the quantity 2x plus 7 and then minus 25. Now this, I'm going to show some extra steps. The denominator just simplifies to this. I can take a 2 out. Now I have this. I have x minus 9 over x minus 9. I'm going to cancel that. And I get this, radical 2x plus 7 plus 5 over 2, provided that x is not 9, right? Because we removed a discontinuity there, if you remember that. So that's rationalizing numerators and denominators comes up. And then the thing that I mentioned was, do not expand the one you are not rationalizing. So if you're not rationalizing the numerator, do not expand the numerator. If you're not rationalizing the denominator, do not expand the denominator. All right, next up. Working with rational expressions. Not entirely sure I picked the best example here. However, This basically comes down to properties of fractions. So we will have complex fraction a over b divided by c over d multiplied by the reciprocal, right? So it's going to be a over b times d over c, which gives me ad over bc. That's one property that you will use a lot. The other one is just adding fractions or subtracting, doesn't make a difference. We have a over b plus c over d. That's going to be ad plus bc over bd. Now, for a terrible example, and I've numbered it number 1 as if I was going to do more, and then I realized this is like a crazy long example. I have just all of this. The quantity x minus 3 squared over x plus 2 cubed minus x plus 2 to the 4th over x minus 3 to the 1st, all over x plus 2 to the 6th over x minus 3 to the 4th plus x minus 3 to the 4th over x plus 2 to the 5th. Why did I choose this? Poor choices were made. All right, what we do is we focus on just the numerator, and we're going to simplify that into a single fraction. So that's going to give me, getting a common denominator, x minus 3 cubed, and then minus x plus 2 to the 7th, all over just the product of those two things. So x plus 2 cubed and x minus 3. All right, now that's just the numerator. Now we focus on just the denominator, and we do basically the same thing. So I'm going to get x plus 2 to the 11th. I'm going to get plus x minus 3 to the 8th, all over the product of those two things. I mentioned I don't think this is a really good example, but it's the one that for some reason I decided to do, and I had a very high sunk cost once I started writing it out. All right, so this is going to give me, I'm going to multiply by the reciprocal. I'm not going to make you watch it. That's the numerator. The denominator, I'm taking the reciprocal, and I'm going to multiply by it. So that's the denominator of the denominator. There's the numerator of the denominator. So I've multiplied by the reciprocal, and now what cancels? Well, kind of a lot of stuff. We have x minus 3 to the 4th over x minus 3 to the 1st. So that's going to cancel. We have x plus 2 to the 5th over x plus 2 to the 3rd. So that's going to cancel. And then I'm going to basically swap numerator and denominator here. So I get the x minus 3 cubed. That's so the numerator here is the numerator of the fraction on the left up top. The denominator here is the denominator of the fraction to the right on the top. That's where that's come from. And then I simplified the numerator-denominator situation, as discussed, and we just are left with x minus 3, x plus 2 squared. What a terrible example. I don't think that was a good example, but it's the one that I chose to do. All right, another thing that you will have to do is deal with lines like way more than you would guess. Lines are one of the most important things to deal with in all of calculus. And so there's a couple things to know about them. First of all, a vertical line. You don't run into that in algebra all that much, actually, but they're pretty important in calculus. It's x equals c, and they have an undefined slope, which means if you were doing delta y over delta x is somehow 0, right? That's what gives you undefined. You will have horizontal lines. A horizontal line will be y equals c, and that, most importantly, has a slope of 0. Horizontal lines are crazy important in calculus because they have a slope of 0. All right, next up, when you're writing lines in calculus, you are going to use point slope form, which is y minus y0 equals m, the quantity x minus x0. You should fall in love with this because certainly if you have me, it's basically the only way that you're going to be writing your lines. Learn to love it. You don't need to work anything out. You just need a point, you need a slope, and you're good to go. All right, how do we find slope? Slope, we usually call m in algebra. It's delta y over delta x, or y2 minus y1 over x2 minus x1. Now, when you're dealing with slope in calculus, algebra 1 slope, it will frequently be called the average rate of change. So average rate of change is algebra 1 slope. You should chant that to yourself over and over again until it's like a part of you. Another thing to know is that a secant line will come up quite frequently. This is literally a line that goes through 2 points. That's it. Do not overthink it. It's new terminology for something you've been doing forever. All right, the next thing that we need to know, function notation. We use function notation a lot. So my recommendation is you want to try to get used to not knowing the function, just knowing about the function. So maybe you'll know a couple of points on the function, you'll know some characteristics of the function, but you won't actually know what the function is. That's where function notation really comes in. My first example, we do know the functions just to make sure you know how to do these things. So f of x is x squared plus 2x. G of x is sine of x. All right, so if you are asked to find f of g of x, that means replace every x in f with whatever g of x is. So that would give us the quantity sine of x squared plus 2 times sine of x. That's all we're doing there. If we had to find g of f of x, it's every x in g becomes whatever f of x is, which is x squared plus 2x. So that would be sine of x squared plus 2x. All right, that's a thing that's a little less common. Now this next problem is what I really think of. So we have a table of values. X goes from 1 to 4. We have some f of x values, some g of x values. We're told h of x is f of g of x minus 3. And the question is to write the secant to h of x on 2 to 4. This is a common type of thing. So I'm going to say I need to find h of 2. H of 2 is f of g of 2 minus 3. Now I need to figure out what g of 2 is. I go to the table. G of 2 is 4. So I'm really finding f of 4, and then I'm going to subtract 3. Now I need to figure out what f of 4 is. F of 4 is 1. So I'm doing 1 minus 3, which is negative 2. And then I need to find h of 4, which is f of g of 4. I need to figure out g of 4, which is 3. So I get this. And then I need to go to the table and find f of 3, which is 2. So I'm really doing 2 minus 3, which is negative 1. And now I just need to find the equation of the secant line. That's a line through 2 points. The slope is going to be 1/2. The secant line, you're going to use point slope. So I'm going to get y minus the y value is negative 2 equals 1/2, which is the slope, x minus 2, which simplifies to y plus 2 equals 1/2 quantity x minus 2. Leave it. Don't expand that. Or you could have used the other point. So y minus negative 1 is 1/2 the quantity x minus 4, which again, you can expand a little, but do not try to solve for y. Don't try to expand things. All right. Next up, functions that I think you must know 100% because they're going to be so useful to you overall. All right, so first up, 1 over x. So 1 over x, it's in the first quadrant, it's in the third quadrant. What are some characteristics that are useful? It has a vertical asymptote at x equals 0. It has a horizontal asymptote at y equals 0. And, although we haven't talked about limits yet, this is an overall decreasing function, and the limit as x approaches 0 from the left is negative infinity, because you're going down to negative infinity. The limit as x approaches 0 from the right is positive infinity. So that's a lot of good characteristics to think of when you're presented with a problem and you need like an example or a counterexample. That's what these are really about. Can you think of a function that gives you the property you need or contradicts a claim? The next step, absolute value of x, right? So absolute value of x, very common function. Most important part here is that it has a sharp turn at x equals 0. It is not a smooth transition like x squared would have. It's a very sharp turn. You're going one way and then suddenly you're going the other way. Very important function. Next up, underrated, y equals the absolute value of x over x. So this function is always 1 when you're to the right of 0. It is always negative 1 when you're to the left of 0, and this function does not exist at 0 because you'd have 0 over 0. Now the key, so this comes up and it's really just good to know. The key feature though, this has a jump discontinuity at x equals 0, and not a lot of functions have that can be written non-piecewise. So that's why you really want to know this one. And that's about it. I mean, I think it's useful to know. It's going to come up. You might see it in a multiple choice question, free response question, who knows? All right, next up, square root of x. Square root of x kind of is what it is. People expect you to know it. It has a domain greater than or equal to 0 and a range greater than or equal to 0. I don't have much to say about that. Next up, y equals x squared. Also, not much to say about it other than it bounces at x equals 0, and that actually is an important characteristic to get used to. It has what's called a double root there, and that's its graph. So so all even polynomials eventually kind of look like x squared, which is what I think is the most useful part. Similarly, y equals x cubed is an odd polynomial, right? And so, I don't know, I guess the most important things about this are the shape of the graph, and as you go to negative infinity, the graph goes to negative infinity. As you go to positive infinity, the graph goes to positive infinity. These are just good to have in your mind. Y equals e to the x. E to the x, exponentials in general, you need to know their shape, and a couple of key things about them. So, for example, this has a y-intercept of 0, 1. Make sure you know that. We have a horizontal asymptote of y equals 0, especially as we go to negative infinity. Actually, only as you go to negative infinity. And then there are two limits that are useful to know. The first one, the limit as x approaches negative infinity of e to the x is 0. That's the horizontal asymptote. And the limit as x approaches infinity of e to the x is infinity because you just keep growing forever. So those are good things to know about e to the x. Next up, natural log of x. All right, natural log of x is a really important function. I find myself drawing this on the board over and over again to remind students of it. Make sure you know natural log, its graph, and a couple of properties. So for example, the point e comma 1 is on this graph. The y-intercept is, the x-intercept is at 1, 0. It doesn't have a y-intercept because the domain is x greater than 0, which I forgot to write down. Vertical asymptote at 0, and we never cross or intercept that. The limit as x approaches 0 from the right, which is the only way you can approach, is negative infinity, and there's an x-intercept at 1, 0. So those are good things. I got 4 more, kind of. So 2 of them you already know. Do I know them though? I screwed up cosine before. Y is equal to sine of x, y is equal to cosine of x. Make sure you know those. Now this next one, I don't know. I think it's important. I think if you do recognize it, it alleviates a lot of frustration later on. It's this, y equals the square root of r squared minus x squared. This is a semicircle, and it comes up in calculus a lot, in particular because you can find the area of it, right? The area of a circle is pi r squared, so the area of this is pi r squared divided by 2. So this will come up quite a bit, and I think it is just useful to be able to recognize this. Now, my last type of function that I think you should know can't really be described because it could be anything, and that is a piecewise function. So piecewise functions could combine any of the functions we just talked about or any other function you can think of. And I would say that piecewise functions, when you think you know something is definitely true, when you think all functions of a certain type have a certain property, you should think of piecewise functions because they kind of are notoriously good at breaking the rules. So make sure you are on top of your piecewise function concept. All right, properties of logs are next. There are not a lot that I think you need to know, but one thing I do think you should know is that basically in calculus, you really only use natural logs, which are ln of x. You don't use other bases all that much. Anytime there is another base, step 1 is to use the change of base formula, which I haven't even included here because I always feel like if a calculus question involves that, it's like, I don't know, like why are we doing that? So I don't include those in my course, but no, whatever. Let's look at the properties. Number 1, the natural log of a minus the natural log of b is the natural log of a over b. So subtraction between logs becomes division within logs. That is more important from a calculus standpoint, in my opinion, than this rule, that the natural log of a plus the natural log of b is the natural log of a times b. In my experience, that is far less used in calculus. So it's that subtraction between becomes division within. You will find yourself using that quite a bit, especially when you're taking limits. That's more of a Calc BC thing, but it does happen. So that's one of the properties. Another property, hugely important, a times the natural log of b. So coefficients can become exponents. So a times natural log of b is the natural log of a to the b, or the natural log of a to the b is b times natural log of a. So it works in both directions. You find yourself using it in both directions. The third thing I think is really important, e to the natural log of x is the natural log of e to the x is equal to x. So it is true that e to the natural log of x is equal to the natural log of e to the x, but that's not like a thing people think about. It's really that e to the natural log of x is equal to x. The natural log of e to the x is equal to x. And so all three things are equal. E to the x, natural log of x, are inverses of each other. That's why they have this property. But this thing will come up all the time. E to the natural log of x in particular, going to come up forever. The natural log of e to the x, we have an exponent that can become a coefficient, is x times the natural log of e. The natural log of e is 1, so that obviously kind of just simplifies, but e to the natural log of x, it's a little less obvious, simplifies to just x, but it does because they're inverses. All right, my fourth property that I think is important, you will not run into all that often as people telling you it's important, but trust me, this comes up a lot, and if more people knew it, it would simplify things. E to the t plus c1, c is just some random number. E to the t plus c1 is equal to c2, a new random number, times e to the t. Now, why is this the case? It's properties of exponents. So e to the t plus c1 is e to the t times e to the c1. But what is e to the c1? It's just some number that you don't know, right? So that, I think, is an underknown, a lesser known, a less commonly known property that I think is important. So I threw it in here. All right. Next up, I think, so if you are going to take a class where they don't expect you to know anything about limits going in, this wouldn't be review. But if you are going to take a class where they expect you to know limits going in, this is review. All right, so limits. There's a couple of things that we can do. I'm not going to go super in-depth with this because it's just like an overview. The first one is you can evaluate a whole lot of limits just by doing substitution. So if we had the limit as x approaches 3 of 3x over 5 minus x, if I just try to substitute in there, I just get 9 over 2, and I am done. Next up, sometimes you have to do some algebra and then substitute. So for example, if I have the limit as x approaches 3 of the quantity x plus 1, the quantity x minus 3, all over x squared times the quantity x minus 3, step 1 is try to do the first thing, try to substitute in, but I get 0 over 0. 0 over 0 is like a mathematical code for try to do something else. In this case, I can pretty clearly simplify the x minus 3's. So if I cancel those, I am left with the limit as x approaches 3 of the quantity x plus 1 over x squared. And now if I substitute in, I just get 4 over 9, and that's my answer. So substitution works frequently. Algebra and then substitution also often works. Sometimes you're going to have to factor. Sometimes you're going to have to rationalize either a numerator or a denominator. That's why that's on this list. All those things. Now, in this category, I would say sometimes limits from a graph come up. Actually, frequently limits from a graph come up. So here's a graph. And what I'm going to do is I'm going to write down the important limits here. So first up, I'm going to approach 2 from the left. So these are one-sided limits. One-sided limits means either approach from the left or the right, but not necessarily both. So the limit as x approaches 2 from the left of f of x is 3. Why? Because if you do it, you approach the y value of 3. The limit as x approaches 2 from the right of f of x is 1. Again, why? Because if you do it, that's the y value that you approach. That's how you basically answer these questions when you're given a graph. The next thing, the limit as x approaches 4 from the left is infinity. How do I know that? I did it. That's all you have to do. Every time you're wondering, just do it. The limit as x approaches 4 from the right of f of x is negative infinity. Again, because if you do it, that's where you're headed toward. All right, and then finally, the limit as x approaches 5 from the left of f of x is 3, because it works. The limit as x approaches 5 from the right of f of x is 3. Now, that means that the limit as x approaches 5, you don't need to put a plus or a minus. You can just say the limit as x approaches 5 of f of x is 3, because the limit from the left equals the limit from the right equals 3. So this is an overview. You're going to do a lot of limits in calculus, but going in, having a sense of them, making sure you've got some of the rust off from the summer, all good ideas. Next up, limits to infinity. So this is as x approaches infinity or negative infinity. So first up, you could have a graph. So we have this graph. In this graph, if I approach positive infinity, the graph approaches 2. The limit as x approaches to infinity of f of x is 2. That's a horizontal asymptote. If we approach negative infinity, the function approaches negative 2. That's a horizontal asymptote. So this is a function that has 2 horizontal asymptotes, and that's just graphically. Now, you could also go to infinity and not have it kind of like level off. So here, the limit as x approaches negative infinity of f of x is just infinity. It can happen. That just means you don't have a horizontal asymptote in that direction. Or the limit as x approaches infinity of f of x could be negative infinity, which means you, again, don't have a horizontal asymptote in that direction. You can mix and match the two graphs, though. You could have no horizontal asymptote to the left and have one to the right, whatever, a lot of options. Now, I'm going to show you 2 algebraic things just for rational functions, because it's just an overview. I don't want to get into the weeds of it. But if we have the limit as x approaches infinity, 3x squared plus 5x minus 2 over 4x squared plus 3x plus 1, what you do here is you take the highest power of x in the denominator and divide every single thing that you see by that power. So I'm dividing everything I see by x squared. That's going to give me the limit as x approaches infinity of 3 plus 5 over x minus 2 over x squared, all over 4 plus 3 over x plus 1 over x squared. Now, if x goes to infinity, everything except the 3 and the 4 just goes to 0, so we are left with 3/4. That is a technique you will find yourself using a lot. And If we do the limit as x approaches infinity of x to the fifth plus 2 over x squared plus 1, I'm going to try the same approach. Divide everything I see by the highest power of x in the denominator, which is x squared. That's going to give me the limit as x approaches infinity of x cubed plus 2 over x squared over 1 plus 1 over x squared. The 2 over x squared goes to 0. The 1 over x squared goes to 0. X cubed, as x goes to infinity, is infinity cubed, is huge. So this answer is infinity. Just because you go through the process doesn't mean you're going to get a finite number. Here we got infinity. It just means there is no horizontal asymptote as we go to infinity. Let's take a look at the next thing, which I do think is a really important thing to walk in knowing. Divide everything you see by the highest power of x in the denominator. That is the technique you want to use. All right, getting on to, I think you should know the limit definitions of the types of discontinuities. There's 3 types of discontinuities. And I think you should know the limit definitions, what they look like on a graph, and generally speaking, where they come from as you walk into a calculus classroom. So here they are. We can have a removable discontinuity, often called a hole in the graph, which is very descriptive. To get this according to limits, you will have the limit as x approaches c of f of x exists. So I don't know, you're approaching 2 from the left and the right, whatever. It's a finite number. The limit as x approaches c of f of x exists, but the limit does not equal the value of the function. Now, the value of the function might be something different, or the value of the function might not exist at all. Does not make a difference. We just need the limit to exist and not equal the value of the function. That's going to look kind of like this. You know, I'm just making up a graph, but it's a hole. It's a removable discontinuity. Now, these typically will come from a factor of the denominator that cancels with a factor in the numerator and just removes the factor from the denominator. That's where you are typically getting removable discontinuities. Next up, jump discontinuities. So a jump discontinuity has kind of an interesting definition. It's that the limit as you approach c from the left exists and is finite. The limit as x approaches c from the right exists and is finite, but they are not the same numbers. And because of that, you would literally have to jump to get from one branch to the next branch. So here's a picture. It looks kind of like that. You would have to jump to get from one to the other. These are mostly just going to show up from piecewise functions. I would say like the vast majority of them are going to show up from piecewise functions, but absolute value of x over x has a jump discontinuity. That's part of why it shows up frequently. It's a very interesting function. Like, go back and review that if you've already forgotten about it. And then we can have the third type. So the third type is an infinite discontinuity. There are many ways to get an infinite discontinuity, and an infinite discontinuity is basically a vertical asymptote. So this means that either the limit as you approach from the left is infinity or negative infinity, or the limit as you approach from the right is infinity or negative infinity. You only need one of them to be true. You don't need all 4, you don't need 2 of them. Just any one of those 4 will give you an infinite discontinuity. So here's on a graph a bunch of them, right? So I don't know, I just drew a bunch, right? As that left-hand thing, as you approach from the left, goes to infinity. As you approach from the right, goes to negative infinity. The right-hand vertical asymptote, as you approach from the left and the right, both go to infinity. Vertical asymptotes, infinite discontinuities. Now, where do these mostly come from? They mostly come from a factor of the denominator that does not cancel. So removable is a factor of the denominator that cancels overwhelmingly. I mean, it could be a piecewise function that's stitched together funny. But generally, removable, factor of the denominator that cancels, and then infinite will be a factor of the denominator that does not cancel. That's it. Those are the things I think you need to know. This is like my ultimate AP Calculus summer assignment topical review. My plan is to make more videos where I'm actually doing problems that utilize these, so we'll see if that comes to pass. But anyway, I hope you found this very helpful, and good luck.